All right, hello and to another Applied Flow Technology webinar. My name is Nick Vastine. I'm a business applications engineer here with AFT, and today we're going to be walking through some different troubleshooting techniques that you can apply to your troublemaking models. So today we're going to kind of run the gamut and we're going to look at a lot of different things. And hopefully it'll start from really foundational things like what kind of approach you should take to modeling and what philosophy you should have as you approach it. What sort of input do we want to look at, output that we can look at, and then how do we experiment to try to troubleshoot, determine an issue, and then figure out how we can resolve that to make our results more trustworthy. So each of these, think of these as different chapters that we'll work through. The first will be modeling philosophy, where a model is only a representation of some physical system or some system that we're trying to build, and we're trying to model that precisely, but our assumptions are inherently imprecise, so how do we try to rectify that? The model is just solving systems of equations, so everyone that's done algebra or calculus, how do we take our inputs, let the solver determine what it needs, and then that we can review as our output. Speaking of those inputs, how do we make sure we understand the concept of garbage in equals garbage out? So depending on the quality of our input, that'll ultimately determine the quality of our output. Regarding our input, some assumptions are going to be fundamental to the solver itself. So whether that's AFT Fathom being incompressible, AFT Arrow being compressible, or some other assumptions regarding transient analysis. What assumptions is the software making, and then what assumptions are you as the user making? Some of those assumptions might be in how you define your model, whether you're using some of the provided handbook correlations, or if you are using a resistance curve, how do you make sure that you're using that properly? And then ultimately, what kind of question are you investigating in your analysis? So what is the intent of your model? What questions are you trying to answer? How do you make sure that you're only answering those questions and not introducing unnecessary uncertainty? After we go through all of our input, we can take a look at our output results. The first question should be, do you trust your results? Do things make sense? A lot of that comes from engineering judgment as well, but there's also indications from the software, like warning messages, that your results may be more questionable. From that output, it's really useful to determine what areas we need to investigate. That can especially be the case if you have a model that's failing to converge, or if you have a particular area where you see an abnormally high pressure drop, or a control valve is failing where they shouldn't be failing. Once we've identified those areas, how can we experiment within the software to try to isolate those issues and then ultimately try to rectify them? Again, trying to make those trustworthy results that we can make those engineering decisions from. So we'll look at how we can use different scenarios and some scenario-specific tools to do that, how we can simplify our model and try to isolate different areas. And then finally, we'll look at trying to achieve convergence through some different methods. So again, starting kind of fundamentally, what is an approach to modeling? How does that impact our input and making sure that that is accurate? Accurate input means accurate output. And when we start to see discrepancies or we start to run into issues, how can we experiment to try to rectify all these different things? So chapter 1, we're going to look at modeling philosophy, where again, we're looking at precisely modeling imprecise things. How do we solve systems of equations? In this case, the software, AFT Fathom, Arrow, Impulse, or xStream, they are what's solving the system of equations for us. And so to make sure that they're providing trustworthy results, we want to make sure we have good input, the concept of garbage in equals garbage out. If we tell the solver a bunch of bad information, it's only going to run the numbers and do the math for us. It can't check our input or our output for us. So what is a model? Again, really starting from foundations, a model is an informative representation of a system of interconnected variables and inputs. So this is stolen almost verbatim from Google, which is a great resource. And in the context of hydraulic modeling, we're going to look at input, solver, and our output. So the input in this case is things that you as the user need to specify. So we need to specify a fluid, whether that's water or air. Those two things are going to behave very differently. Pipes, whether that be the pipe's length and the diameter and the roughness, things like that. And then also boundary conditions. So we'll talk a little bit more about boundary conditions on the next slide, but think of them as drawing a control area around our system. We have to specify either a pressure at that point or a flow rate at that point. And depending on what we specify, that can change our results as we start to experiment and make other changes to the system. We feed all this input into the solver. Again, this is starting from fundamental physics equations or from correlations from things like friction factors. And we can solve basic mass, momentum, and energy balances to make sure that no laws of physics are being broken. And by solving those equations, we can get our output. So some of this output is also going to be input in the form of boundary conditions, but ultimately, as an engineer, we're looking for things like our pressure, our flow, and our temperature distribution. So I like to think of modeling as breaking it into these three parts, and we want to make sure that if we're troubleshooting, that all of these parts independently are going to be quality, and that way we can trust our output, we can trust our results, and move forward with our analysis. So a model is only as good as its input. However, we don't know everything. So for example, you might not know how old your valves are, or if they've decayed over time and aged, or if you have scaling in your pipes, things like that, if the roughness has changed. Or if you're kind of approximating your model, let's say you're looking to construct something and you want to check the hydraulics before you build it, then you might rely on other things to feed that input, give the solver something to solve for, and then provide the output that you're looking for. So you might rely on correlations, handbook data, heuristics, or other simplifying assumptions. So it's important to recognize that those assumptions are being built into your model and understanding the implications that they might have on your output. Again, your model's only as good as your input, and the software cannot verify your inputs for you. So it can't tell you if that pipe should be 5 feet instead of 6 feet or 5 meters instead of 6 kilometers. It can only take the inputs that you've provided, plug that into the solver, and provide the output that it's asking for. So garbage in equals garbage out. How can we make sure that the input to the model is as good as possible, and that ensures that our output is also trustworthy and as good as possible? It's important to always use engineering judgment. Again, the software, you can think of it as kind of omniscient. It doesn't have a mind of its own. Ultimately, it's just a calculator that you're plugging numbers into. So you have to make sure that the calculator is working properly, and also the numbers that you're plugging in are working properly. So that's kind of the background of modeling philosophy. Let's take a look at these boundary conditions, because this is also important, and this is also a common stumbling block where new users especially might have information about their system, and they're trying to define everything at the same time. So in terms of input, let's say that we're looking at a case where we have a model and we know the flow rate and we know the pressure at a series of different points. We might have that from field data, or we might have a previous model that we're looking at, and we're trying to establish a baseline for our system to meet these pressures and flows that are occurring in the field. However, we can't do that because we're over-specifying the system. So if we completely specify at every point in the system the flow rate and the pressure, then there's nothing for the solver really to solve. This can be challenging conceptually, so let's look at a more simple example. Let's say that instead of our hydraulic system, we're trying to calculate velocity or the distance traveled over time. So here we have our input, which is our speed and our time. Our solver in this case is going to be a simple equation where the distance that we're solving for is the speed times that time, and our output is how far we've gone. So let's say that we're looking at a case where we know how fast something was going, we know how far it went, and we know the time it took to do that. Here our input would become speed, time, and distance. And now if we try to plug that into the solver, we don't really have anything to solve for. So we've overspecified the system, and it might also be a case where the speed, time, and distance, if we run this calculation, it might not be equal. It might not be a valid solution to our system. And it also fixes all of our variables so that when we make changes, you're overspecifying and it can't iterate or solve on that remaining degree of freedom. So we can think about this the same way in our system, where our boundaries either have to be a pressure or a flow rate. We can't define both. And how we define those boundary conditions ultimately informs our assumptions about that system. So here, for example, we have a collection of flow rate junctions and pressure junctions where all three of these systems could provide the same results. We can have the inlet pressure and the outlet pressure that can cause a flow. If that flow is equal to these flow rates, then this inlet pressure will equal this inlet pressure, this outlet pressure will equal this outlet pressure. So depending on how we're defining those boundaries is informing how we're defining our system. So as we get into scenarios and we start tweaking the system, what if we added a valve in the middle, for example, and the valve is half closed? Here we're assuming that no matter what, we're going to achieve that flow rate, so our pressure is going to increase, or here we're going to achieve that flow rate, so our pressure is going to decrease, whereas here our flow rate would instead decrease. So by setting these boundary conditions, we're essentially telling the solver what degree of freedom or what variable, whether that be pressure or flow rate, can vary. And that's ultimately what the solver is good for determining what that output should be. That's why you're doing this instead of just saying, well, I know I need this pressure and this flow rate in this pipe. So if I build a model and I specify it there, I know that I can guarantee that in the physical system. Something common that you might see or you might do yourself, especially if you are kind of introductory in your modeling skills, is again coming back to this case where you have field data where you do know the pressure and you do know the flow rate at a range of different points. What you might try to do is assign a pressure at a point, and then you'll add a flow control valve, where the flow control valve, that's what's setting your flow rate at that point. So now, downstream or upstream of this, you're matching that field data, which might feel good, but what you're doing is you're introducing essentially another boundary condition into your model that wouldn't exist in the real system. So if you don't have a flow control valve in your physical system and you're just using it to try to calibrate and match systems, generally that's not a good idea, because again, imagine if we're trying to add a valve or we're trying to open or close a valve slightly, this flow control valve is always going to set the flow rate at that point. Instead, what you can do is try to change other aspects of your input. For example, you can add a design factor or you could increase the roughness. That way you can maintain your pressure boundaries, you can achieve the flow rate, and things like those variables like pipe size or internal scaling or roughness, all of those things should stay the same even when you make other changes to your system, like adding a valve or trying to open or close it. So it's very important to understand these boundary conditions because again, garbage in is garbage out. You're going to hear that a lot throughout this webinar. And so by defining your system, you're inherently making assumptions about at the edges and at the boundaries, is this fixed as a pressure or is this fixed as a flow rate? And when I make any other change to the system, whether that's swapping out the pump that I have or valves or opening or closing different lines off, will those boundary conditions be maintained? And we want to make sure that we're not trying to create boundary conditions just to meet field data. We want to make sure that it is going to transmit through any other changes that we make in the system. So boundary conditions, very important. Obviously why it deserves its own slide, but we're all here for troubleshooting. So when you encounter an issue, how do we try to compartmentalize the problem with our model? And we can do that again by thinking in terms of input, solver, and output. So from the input perspective, again, this will be the second chapter where we look all about input. What assumptions are you making? How are you defining your model? And what question are you investigating? From the solver, what could cause a convergence issue? Are you on the edge of the solver's capabilities? And then are you breaking a solver assumption? For example, is your liquid flashing breaking the incompressible assumption, or is your gas condensing and breaking that compressible assumption? And then output, again, do you trust your results? What are the warning messages telling me? And then where is your area of concern? So we will take it from the top. We'll look at how we can review our input. Garbage in equals garbage out. We can all say it together at this point. And so we want to look at what assumptions we're making. How are you defining your model? And then what question are you trying to investigate? How do you make sure that you're only looking at the variable that you're interested in at a time? So what kind of assumptions are going to be inherent to the software application, and then what are going to be inherent to your analysis, or things that you might decide are assumptions for your analysis. So incompressible versus compressible effects, you've already made this choice whether you're using Fathom or Arrow. So that's one inherent to the software application. Heat transfer may be negligible. So this might be a harder sell as an assumption when you have compressible fluids, where heat in might expand the fluid, or heat out might de-expand or compress the fluid a bit more. That'll change how fast your fluid is flowing, the losses that it sees, impacting the pressure. And again, all those equations of state are all related, but it's an option. You can simplify your model, eliminate heat transfer, and see if there are any consequences to your results. This point is specific to transient events. So you might look at something called a slow transient, which in AFT language means that with any change to your system, it immediately achieves a new steady state. This is different from a fast transient, which you might model in AFT Impulse or AFT Xstream, where you want to model the sudden pressure rise or the sudden change in flow rate from something like a pump trip or a valve closure or a relief valve opening. So what assumptions go into each of those? Again, if you can capture it as a collection of steady state snapshots, you can model it as a slow transient, or if you need to see how those pressure waves move throughout the system, you might need a fast transient solver with Impulse or Xstream, whereas slow transients would use the extended time simulation module, the XTS module for Fathom or Arrow. We also want to make sure that the features that we're using within our models are appropriate. So for quadrant analysis, what that does is it allows you to more precisely model a pump during reverse flow events. And as we saw in our boundary condition example, you might use control valves where there aren't any. So that would be an inappropriate use of a feature. Or if you're trying to use four quadrant analysis and you don't see reverse flow, you may be better off using a more traditional pump curve. So again, taking a step back, making sure that the features that you're using are appropriate and are actually modeling the behavior that you're trying to model. You can use design factors to provide engineering safety margin. This also depends, especially in water hammer or transient analysis, where something that may be conservative in one scenario or one set of analysis might not be conservative in another. So it's important to understand those implications. And if you do have design factors, recognize that how you're modeling it and how you're going to build it, you're inherently going to see different results. But hopefully, as you're making your design, you're using engineering judgment and you are making sure that it's a conservative estimate instead. Finally, you want to make sure that the information you're entering is accurate. That could be a very big assumption, and something that we want to look at today is before you do anything else, you want to double check your input. Then you can start being worried about the solver or about the software reporting something incorrectly in output. Again, garbage in equals garbage out. How do we make sure that the input itself is good? So you might pull that from P&ID documentation and spec sheets, where these could add their own uncertainty. These might not necessarily be accurate, especially if your pump has been derated or is aging and doesn't perform at the same rate. If you're using things like handbook losses, which can be provided by AFT, and then also fluid data and mixtures, how are you ensuring that the fluid you're modeling is accurate? Speaking of accurate input, now we can look at how are we defining the model. And here's where we'll start jumping into the software and looking at these different facets of where to look. So the first place I would check is confirming all of your information is accurate, and I would use the model data tab. So this is great for looking at things like units or ensuring that your pipes are the intended sizes and lengths. The relative magnitude of these things is relatively consistent. So you might have a 3-meter pipe next to a 3,000 meter pipe. That might not be unrealistic for a pipeline system, but might be unrealistic if you have a smaller refinery system. You can check your control set points for your different control valves, and then you can also look at fittings and losses. So if we take a look in the software, here we have an AFT Fathom model, which is one of our example files. And here we have a collection of pumps going through a pair of control valves through some heat exchangers, and it recirculates around. So what I would do is look in this model data. We'll zoom in a little bit so you can see a bit better. Here at the top is the general tab where it has some information about your solution control. So here the pressure head tolerance is relatively low. In general, if you're building the model yourself, there shouldn't be any changes to solution control, but especially when someone's trying to troubleshoot or running into problems, they might get desperate and go change those. You can look at your fluid information as well, especially if this is custom fluid. You want to make sure the units of that are correct, and then making sure things like your density, viscosity, and vapor pressure are reasonable. So that's a general tab. Also, if you have any notes defined in your model, those will also appear here. If we look at pipes, here we can see at a glance all of our different units. So we can see the majority of the model is defined in meters, and here we have a 90-kilometer pipeline. So we look at our model, we can see pipe 20, and here we can see this long pipe. Based on the scale of the model, obviously how you've drawn it in the workspace doesn't really matter, and it doesn't inform your output and your calculations, besides the different connections that it makes. But it looks like this could be an area of misinput. Same thing with this 15 millimeters, or vice versa, if 90 seems unreasonable, you could look at the length, and if it was more extreme, it might be more skewed the other way. Similarly, we can look at our different pipes. So here everything looks pretty reasonable, either 4 inches or 6 inches. And then we can also look at the losses defined in the pipes. So here in that same pipe 20, it's almost like I made this as an example. We can see that they have a very high amount of loss in this pipeline. What we can do from model data, instead of trying to go and find it on the workspace like we have here, we can double click, that'll open up the properties window, and here we can go and investigate. We have a globe valve, and then we also have an additional K factor of just 100. So model data can be really useful for trying to isolate these things, and also look at these fittings and losses where it isolates that, and it'll list all the fittings that you have. And then we can also do the same thing with junctions, where we have different specifications for our bends, control valves, heat exchangers, our pumps, and then our reservoir. So if we're thinking back to our boundary conditions, it's very important to make sure that this is defined correctly, so we can go and check that we have a liquid elevation specified in this case. So model data is really useful for pipes, but it's also really useful for looking at influential junctions. What I would consider influential is things like pump curves, where how that pump is defined is going to inform a lot about your flow rate, and it'll be much more sensitive than a valve state or a valve K factor, for example. Boundary conditions, as we saw looking at the reservoir, resistance curves, which is a way that we can represent losses in our system, and then also special conditions. So for example, if we have a control valve and it's failed open, how do we make sure that that is being modeled accurately? So again, back in Fathom, from model data, we can look at things like RTs. And here we can see a kind of anomaly where we have one detailed T, and we can see that it's T11, which is over here. If we open that up, here we can see that it's showing the T vertical and with a pipe to the right, which is not representative of our system. And as a result, a lot of these pipe combinations might not be accurate. So one of the common pitfalls that I'll mention is detailed T's in particular, is making sure that this aligns with this setup. So if we click this auto arrangement down here in the right, we can see that it does match with what our workspace has defined. But also detailed T's add kind of another iteration loop into the solver. So one of my suggestions would be, how can you model simple T's, try to get the model to converge, especially if that is the concern, and then you can look at the impact of those detailed T's in a different scenario. Here we'll cancel out, we'll leave it as broken, as intended. And we'll take a look at these heat exchangers as well. So in these heat exchangers, we can see that the loss model is a resistance curve. And that should be a flag because there's an opportunity to misspecify what's going into a resistance curve. The same way that a pump curve is reliant on a series of points that we can curve fit, the same thing is true of a heat exchanger. So if we look at a heat exchanger, think of this as the heat exchanger is creating pressure loss as we flow things through it. So at a 0 flow rate, we should see 0 pressure loss. There's no friction and there's no turbulence to create a pressure loss. And as that flow rate increases, we see a quadratic increase in this pressure drop. So this is what an ideal resistance curve should look like, a quadratic fit and then intersecting at the 0, 0 point. But you might also run into cases where you want to model a fixed loss across many different flow rates, again, depending on how you've measured it or what assumptions you're building into the model. So here in the same heat exchanger, we would expect these two to be the same. And if we look at this graph, we don't see that same quadratic pattern. Instead, we see a fixed pressure loss at a lot of different flow rates. And this can also lead to issues with convergence, especially in a much more simple model where at any flow rate, it's trying to cause the same pressure loss. So here, this is kind of fundamentally breaking physics, right? So if you're creating pressure loss at 0 flow, that's an indication that it's not caused by friction and it's not caused by turbulence. And so this should be a big red flag, especially as you're double checking a model to make sure that your results are going to be accurate. The same thing goes for pump curves, where again, you want to make sure that it's seeing the same downward pattern, capturing this kind of first quadrant where it can operate on any point on this curve. You don't want to see an upward increase in DH overflow, because then the pump would essentially shake itself apart, be able to just add more and more head, creating more and more flow, and it would, I don't know what would happen. I don't think that could happen physically. So not a major concern. Then finally, with control valves here, you can also check your set points. So if we merge this back over, here we can see our control setting. We can see that they're flow control valves. And in our case, that's exactly what we want to be modeling. So those are what I would consider the influential junctions. So as you're reviewing your model, those are kind of where I would start to make sure those things are correct before trying to look at individual pipes and fittings and losses and things like that. We can also use a new tool called the scenario comparison tool. What this can do is indicate what variable we're testing in different scenarios. This can be really useful when you have one modeling case that's working and then another one has issues, where you can see the differences between your two models and identify what is causing that issue. So here in our scenario tree on the right, we have our base scenario, and then we're testing a bunch of different pump speeds and pump impeller sizes. And then in those different cases, we also want to see if pump A is off. So what we can do is from the tools menu, we can go to scenario comparison tool. This brings up all of our different scenarios. If we wanted to be exhaustive, we could select all of them. In this case, we'll look at just the different speeds, and then we'll make sure that pump A is off in this first case. If you wanted to get finer resolution and kind of reduce the amount of things that you're looking at, you could control what pipes and junction properties you're looking at. But we have quite a few different tools in here that will only report if there is a difference. So in general, what I would do is report on everything. That way, if there is a difference, you're aware of it instead of assuming that, oh, there's no differences in any of the bends in my model. So we can look at all sorts of things, whether modules are active, the fluids, and then also what pipes and what junctions that we want to compare. So here I have my selection. If I click show comparison, here it's only highlighting the differences. So let's say we do all for all items. Here we can see across all of these different pipes and junctions that there are no differences. And so to simplify it, we can highlight just the differences, and that'll reduce the amount of information that we're looking at. So here we can see between the base scenario and this first scenario, they're the exact same. We can tell because unique value should be highlighted. So here in pump A off, we can see that the special condition is that this pump is off. So I would say this pump or this scenario is working as intended. Here we can see how some other pump parameters are changing. So the name and the configuration is changed. That's good because again, these scenarios are just comparing what different pumps are doing. Here we can see how something maybe unsuspecting is the heat exchanger has changed in this scenario, and then also the fluid has changed. So use of the scenario comparison tool can be really convenient. Again, if you have a case like all of these other things are working properly and the output of this one is crazy, we can quickly make a comparison, identify what differences there are between the scenarios, and that ensures that we're only testing our intended variable at a time. Again, that's accessible from the tools menu, scenario comparison tool. Very convenient. So some other common pitfalls that you might run into in your model, this would relate more to running into convergence issues, but some things that we might look at when someone submits a support model and says, why isn't my model running, or why is my output kind of strange? A common one is detailed T's, again, because it's adding kind of a different calculation and a different iteration loop to calculate losses within the T's, whereas simple T's just say that they are completely lossless and they fix the pressure at that point. If you run into pumps in parallel, a lot of times because they have all of those curves, again, you're adding an additional variable of trying to solve, and they can kind of fight each other and run into trouble trying to find a solution. You might have mixtures with a lot of different components. That can lead to very slow runtime, and that's something that we'll look at in a Arrow model in just a moment. And then finally, overspecifying the system, thinking back to those boundary conditions. Are we making sure that we're making good assumptions and the solver is able to solve for the variables that we want it to solve for? Try saying that 5 times fast. That concludes our review of input. Now we'll take a look at reviewing output. So should you trust your results? How do you understand what warning messages are trying to tell you? Then how do you identify areas to investigate? So trustworthy results, again, let's think about the software as just an impartial calculator. All it's doing is taking the input that we've provided, solving a system of equations, and providing that output. It can't tell if a solution is accurate to a physical system. It can only tell if, based on your input, assuming that that is accurate, then these results should be what you'll see. So here's an example of real results that you can create in AFT Fathom, where we have a positive static pressure and a lower static pressure that'll drive flow. But we see that that pressure dips to about -70 psi-A. And again, that's negative absolute pressure, sort of like a negative absolute temperature. It doesn't really make sense, right? But from a mathematical perspective, from a solver perspective, it's pretty much creating energy and saying that as it goes up and over this hill, the pressure is going to decrease, and it's going to decrease by this amount. It's more valuable to tell you this and say that, well, it's going to go lower than 1, the vapor pressure, or 2, below 0 absolute pressure. And from that, you can hopefully troubleshoot your model, realize you misspecified an elevation or something, or realize that the model itself and the system won't function. So the accuracy of your solution depends on a few things. 1, input accuracy, garbage in equals garbage out. Sound like a broken record. But also the solver tolerances itself. So depending on how it's approaching solving that system of equations, if you have very loose tolerances, it might not converge on a very good solution. Also from a modeling perspective, especially when you have an existing system that you're trying to replicate in a model to make representations or make recommendations for and changes, you want to make sure that you're accurately calibrating that system first, making sure that you're not using things like flow control valves to fix flow rates. And that ensures that when you start making changes, when you're evaluating new pumps or new valves, that all of those other conditions are going to stay the same. Your pipes are going to be just as scaled or just as rough. The elevation of all of those things is going to stay the same. So it's important to take the time to calibrate, and that ensures that when you make changes, you're going to make quality recommendations, and it should work in that system as it's been constructed. Another case, this is more specific to transient analysis, where your results may start accurate and then they can become less accurate over time. This again comes back to the different assumptions that we're making during input. So for example, when you have cavitation during a transient analysis, where cavitation is the formation of a vapor pocket because the fluid pressure drops below the vapor pressure, the fluid vaporizes, creating a vapor pocket. That creation of vapor fundamentally breaks the assumption of AFT Impulse that it is essentially incompressible, where it's a liquid system. And so as you have pressure waves traveling through it, that can create uncertainty. The collapse of those cavitation pockets can also create noise, and that noise can make your results much more questionable. So having an understanding of how those things can happen, and also as things go on longer, especially with transient analysis, it may become less certain just because it's getting further and further from your initial condition and your initial set of assumptions. But in general, usually in Fathom and Arrow, that's less of a concern just because you're modeling a single point, and so it won't get less accurate over time. Understanding warning messages, all right. So a lot of cases, something you might run into yourself is when you get a caution or a warning message, your first impulse is, my model is bad, I shouldn't trust these results. How can I get rid of these as easily as possible? And that'll make sure that my results are good, right? But by solely getting rid of those cautions and warnings, you're not really addressing what those cautions and warnings might be telling you in your system. And often these messages will reveal important information about what's happening. So if we look at some examples, skip ahead a little bit. At the bottom, we have warnings and cautions from an AFT Arrow model. The lower one is a caution. So the pipe 2 length is shorter than the elevation change between the junctions that it's connected to. Essentially, it's saying that it can't bridge the gap between the elevation that you've specified, but mathematically, it can still figure out the change in pressure due to that change in elevation. A caution will be different from a warning, where a warning will tell you that there are impacts to your model. So for example, here we can see that the fluid is condensing, breaking one of the core assumptions of Arrow. If we think about our system, think about pump system, valve, all of that is all going to be interrelated. So any issue that you see at one point in the model can have consequences that broaden across the entire model. If you see condensation very early in your system and then it might get resolved later, that's going to seed uncertainty because you don't know if the pressure losses at that point are accurate and if you can trust the starting pressure for the rest of the model, for example. Same thing with something like a control valve failure, and we'll look at some other more extreme definitions of cautions and warnings here in a moment. But the two big things to take away is don't try to just get rid of cautions and warnings. And because the system is so interrelated, anytime that you see a warning or a caution, you should look at it because it can have an impact across your entire system. So what types of messages do we have? There's both cautions, warnings, and then critical warnings. So a caution is an indication that something in your model may impact results. So something like the pipe being shorter than the elevation change, sure, that's less than ideal, but it'll still model the change in elevation. It'll still model the pressure losses due to the length of the pipe. Some other examples include negative flow may result in incorrect loss factors. So for example, if you're pumping fluid through in the positive direction through something like a globe valve, that will give you one K factor. And then if you flow through the other direction, that'll give you a different K factor. The most extreme example would be a check valve, where there's only some resistance in the forward direction, and then you have infinite resistance in the negative direction when the check valve closes. So again, it may indicate or it may impact your results, but it's important for you to check and make sure. Pump performance may be impacted by viscosity. This can be triggered by a few different things. It might be triggered by a low Reynolds number, for example. Or if you do have a very viscous fluid, you may want to try to derate your pump and ensure that that's being modeled accurately. Again, these are different from warnings, which is an indication that something in your model will impact results. So something like condensation, you're breaking one of the fundamental assumptions of the model, or you're adding something to the solver that wouldn't be represented accurately in the physical system. So some other warnings is the control valve could not control, pressure was added. For example, if you have a flow control valve set at 10 gallons per minute, and if it fails fully open, the maximum flow rate might be less than that 10, let's say it's 5. In this specific case, the control valve will add pressure to try to create that 10 gallon per minute flow rate. Again, a valve adding pressure is not going to occur in your physical system, but it's a good indication to you as the user that this control valve might not be properly sized, or something else is questionable in your system, especially if you're modeling it based on field data. Another warning is these results do not represent a converged solution. So generally, you'll only see output when you do see a converged solution. By converging on it, it means that it solved that system of equations within what we consider a reasonable tolerance, or the changes between iteration are so small that we've settled on a solution. But in some cases, we might present results that are not converged, and that can help in troubleshooting as well. It can indicate where problems are happening or where strange things might be happening, especially true in something like AFT Arrow, for example. So it's always important to read the warning messages. If you ever run into a warning message that you don't understand, one great resource is our help documentation. So at any time within the software and new to Fathom 12, Arrow 9, and Impulse 9, if you go to help and open help, what that will do is open up our web portal with all of our documentation. Here we'll open up the Fathom homepage. And here we can see all sorts of different resources that we can find. So we have the support site, online resources if you want the latest release. We can look up warnings. And here we can see critical warnings, warnings and cautions, where it'll break down, again, the same information that we just went over, but it'll also list all of the different warnings that you can see. So if let's see, pressure sustaining valve cannot control pressure at this point, saying that it's not able to control pressure and backflow may have occurred. And a lot of the error messages should be relatively intuitive as well. You can also do other things like look up troubleshooting. So if you're interested in troubleshooting, you wouldn't be here if you weren't, right? If you look that up, here we also have a list of recommendations. Again, how do you use the model data window to check your input? How do you look at pump curve fits or resistance curves? Detailed T's, and then some other things for solver improvements. So a lot of what we'll talk about today, a lot of that is kind of textbook and following along with the help information. So this is a great easy access reference instead of coming back to the webinar and looking for where I talk about it. So the documentation is very useful, very helpful, and if you aren't aware of it, it's a great resource not only for troubleshooting, but for understanding what the software is doing. So how can we use the software to identify areas to investigate? The first is warning messages. So we can see in those warning messages, it will tell you where in the model those issues are occurring. So we'll go into the software, we'll say goodbye to our Fathom model, and we'll bring over our Arrow model, but all of these same concepts will apply. Here we can see all those warnings where we've got condensation occurring in all of these different pipes. So if we split this and go to the workspace, we can double click here and we can see how it highlights that pipe. Similarly, if we don't want to expand it, we can double click and it'll bring us to that pipe in the workspace. Again, if you imagine you have a massive model, it can be very convenient to quickly bring you to that point. Some other ways that we can look at our output to try to identify areas is we can sift through our data. From output, we can right click and sort our different information. This can be really useful if you're trying to identify areas of high pressure loss. So you can right click the DP stagnation and sort it in ascending or descending order. You can do something similar with your junctions as well. You can use visual report to associate input and output to different locations in the model. So if we look at that, here we can use that visual report tab. Here I have one already defined with a color map. So above this pressure loss, I want that to be highlighted red, and everything else seems to be okay, less than this 0.06 bar. We can also show near the pipes themselves where that DP drop is and how big it is. And then we can also customize what other information that we want to see. So if we want to know the mass flow rate as well, or the temperature loss, we can show that as well. And that makes it just very convenient to look at in the context of our system. We can go and look at these specific parameters, or from a color map, we can see at a glance where temperatures are high or where temperatures are low. Thinking back to the input portion of the webinar, we can also make a visual report for input instead. So if we click input, we can specify things like the pipe length, the material, and the nominal size. And if we show that, this is another easy way to make sure that in the context of the system, all of these lengths are reasonable, all of the pipe sizes are consistent. So this header, that's 12 inches, and this kind of draw line, that's 3 inches. Again, you would expect those to be relatively consistent with one another. So useful for checking output, useful for checking input, and then as you go into other scenarios, it should similarly report that as well. Last thing is from the workspace, you can also review your information. So this might be more convenient instead of trying to create a very overwhelming visual report. Instead, you can go to the workspace and you can see all of your output specific to a pipe or to a junction. So from the workspace, here, because we have output, we can do this, but you can also check input this way. Let's say we want to look at our control valve. So by holding right click as we look at it, we can see all of our input information, the elevation, it's a flow control valve with its control set point, what its full open CV is, and then we can also look at our output. So we have the inlet and the outlet pressure, how much pressure loss it's causing, and then the temperatures as well. And all of this is customized the same as your output control. So in output control, you can control all of these different variables that you see, and you can do that from this output control button. So if you click up here, here's all the other additional variables that you can consider, and you can also add redundant ones. So for example, if we have velocity at the inlet, you can see that we also have the inlet velocity here. And if we add that, you can add it as a separate unit set. So let's say you're working with international and you're working with different teams in different places. Someone is used to inches per second. I don't know why anyone would, but maybe you are. Here we can see how both of those are represented at the same time. And then when we go and look at a pipe, if we right click it, again, we can see that velocity in meters per second and that velocity in inches per second. So it'll match that output control. So once you get that all set, then it's very easy to come into your model and try to identify what areas you're looking for as you're troubleshooting, making sure that things make sense. You're not creating massive pressure drops where you shouldn't, and you're not having no pressure drop where you should have some, right? So those are a few ways that you can identify where in your model issues might be occurring, again, relying on that output. The final thing is for convergence specifically. So if you have a model that's running for many, many iterations and taking a relatively long time, what you can do is use what we call the iteration history, and that can identify where the solver has gotten stuck. So here you can show the different pressure iterations and the flow rate iterations. And then it'll also tell you out of these pipes and junctions, which is the most out of tolerance or which is the furthest from converging. So to do this, we'll do a little example about fluid databases as well. So here we have AFT standard methane, where all I'm doing is modeling methane according to what we've provided as our database. If we run that model, we can see that it takes roughly 2 seconds, right? But in this case, let's say that we're modeling a natural gas system. Sure, natural gas is primarily methane, but what would be the ramifications of a more complex system? Again, if we have that information, it's an engineering tendency to try to push that into the model, which can be great for final engineering decisions, but can be less great when you're trying to troubleshoot. So when we look at our system properties, here we see that same collection of fluids, primarily methane, and then we have other components including ethane, helium, propane, hydrogen sulfide, and some nitrogen. And so here we have 6 components that we're trying to manage in addition to our normal pressure and temperature and flow rate solution. So when we go to run this model, it looks like it overwrote the fluid, so let's hit OK. And now we can see instead of our 2-second runtime, through our first iteration, we're already at 6 seconds. So this can keep running. In our case, we'll cancel it real quick. And there's a few things that can cause that slow runtime and that gradual convergence. This fluid is a very typical case. You can remember this as one of our pitfalls, the others being parallel pumps or closed loops and detailed T's. So it's a good idea to look at a model, especially when it's running slowly and you're trying to troubleshoot and you're quickly iterating and experimenting, to look at this fluids, see if you can simplify it, and then that'll give you very good returns on your runtime. Here, remember, we're looking at iteration history. So how can we see where in the model it's failing? In this case, I wouldn't worry about it. It wouldn't surprise me that something with many more components is taking much longer to run than something with just methane, and especially between AFT standard and a, I guess, more complex fluid database. But we can still use this as our example to track these iterations. So within analysis setup, here on the left, you can look at steady solution control. And here we can look at our iterations. And here we can check this button to keep track of our iteration history. What that'll do is with each iteration, it'll tell us where in the model it's the most away from our tolerance, which can be useful, again, when you have detailed Ts or parallel pumps or loops, and your model doesn't seem to be converging very quickly, even though it's iterating very quickly. So here's this iterations. If you are in an older version of our software, then you would go from that analysis menu to our steady solution control. So now if we go and run the model again, we see our very slow iterations. It's ticking up very gradually because it has to calculate all of those fluid properties for a range of pressures and a range of temperatures that it's experiencing. If we pause it, we can go to other actions, and here we can see that history. So here we can identify that junction 2 and pipe 1 are where it's struggling to converge, where figuring out how this branch is going to work, that's typically much more challenging on the solver, because you can imagine that now it has another system of equations that it needs to meet. All the mass in has to equal all the mass out, and all the energy in and momentum in has to equal the energy and momentum out. So we'll let this continue to run just to prove a point that if you're troubleshooting and you're waiting minutes between runs, then the return to runtime is worth the trade-off with accuracy. And you might be able to simplify your fluid, and that'll speed up your iteration process. So again, just with that 6-component mixture, not too complex. We'll take a look in the next section how that'll impact your results. So this is kind of reading ahead and looking at some of the ways that we can simplify a model. So here we can see 50 seconds instead of the 2 seconds it took before. So an order of magnitude difference. And then we'll take a look at how our output will compare in the next chapter. So keep you enticed, keep you engaged. That way you don't leave before the webinar ends, right? So most often this iteration history will indicate areas where detailed loops or detailed Ts are running into problems, where there's loops if there's multiple parallel pumps that are trying to fight each other. And then especially when there's many different control valves in parallel, which might be more of an indication that someone's trying to overspecify the system, or you may have that many control valves in your actual system and you just need to figure out how you can make your model run with that in mind. This brings us to our 4th and final chapter, experimentation. So now we know where to look. We've double checked all of our input. Now how can we experiment to see, one, the sensitivity of our results to some different things, and then trying to make a model converge. So we'll look at how we can use scenarios for those cases, how we can simplify our model, for example, with the fluid databases that we just looked at, and then how do you achieve convergence. So scenarios. We already took a look at how the scenario comparison tool makes sure that we're only looking at our intended variable at a time. So we want to make sure fluids aren't changing randomly or any other valves or components are changing. We just want to make sure the one variable we're testing is changing. Scenarios also enable you to explore any effects to isolate a cause of issue. So a lot of those same things that we looked at, fluid properties, heat transfer, whether that's on or off. If we turn off detailed Ts, does that allow our model to run? Are our transient events defined logically, especially if it's defined as a criteria? Is it meeting that criteria? And then you can also look at the sensitivity of different variables. So if you add a design factor or change the roughness of something, how does that impact it? Or if you change the fluid properties, how would that impact it? So tools like Global Edit can make mass changes very simple. What that does is you can select all of your different pieces, go to global edit, and then you can apply that change across all different things. The most common example will be detailed versus simple T's, where you can select all your T's, make them all simple in child scenario, and then run that and compare your results, and hopefully it'll converge a bit easier. So we'll quickly look at global edit. So you could, for example, change all of these pipes, highlight them all, go to this global edit icon at the top. You can do it for pipes or junctions, where any of these pipes we want to push our change to. We can select our data, and these would be the changes that we would make to these pipes. So let's say I wanted to make them all 10 meters long. Then we could say that all of these should now be 10 meters, apply our change, hit OK, and then we would see that all of them are now 10 meters. Obviously, that's not a great application. Maybe looking at changing pipe size or changing the thickness of insulation, that might be a better use of global edit, or that detailed T to simple T, as I mentioned. So we can also use things like multi-scenario output and multi-scenario graphs and the visual report to try to identify these areas, or try to understand what the changes we're making are doing to the system. And so we'll do a quick demonstration of this multi-scenario output. So here's the output specific to our scenario. If we go to that output control, the same place that we change the variables that we want to look at, we can go to this multi-scenario tab. We can select the different scenarios that we want to compare. And here I want to isolate the impact of using AFT standard methane compared to our natural gas. So here we can see in white the standard methane, and then in orange we can see the natural gas. So 90% of our fluid is methane, and so we can see that the pressure drops are pretty consistent with one another, and then the mass flow rates that result are also pretty consistent with one another. So especially as you're first building the model, it may be better to start with a simpler fluid and then get more complex in your later runs. Or if you're doing troubleshooting, going the other way, simplifying your fluid, and that allows you to quickly iterate and quickly model your system. You can do the same thing with graphs. So you can do multi-scenario graphs. In this case, we'll look at AFT Impulse instead, where here I'm doing a comparison of different valve closure times from a half second all the way up to 30 seconds. If I go to my graph results, I can make a transient valve graph where I want to look at the valve CV, and I want to look at the inlet pressure in this case, and then let's also look at the flow rate. So if we hit generate, here we can see in the half-second case, the CV dropped very significantly. That causes a pressure rise and our flow rate to drop. Here we can click this multi-scenario button, and what that'll let us do is select all these other scenarios we can look at. So I'll say all. Now if I hit OK, we can generate that. And here we can see how those different CV closures result in a very different pressure rise seen by the system. So you can do different time closures where you could look at different types of valves and how that would impact it as well. But again, if you're trying to troubleshoot, it's very easy to take something that you know works, make a graph, compare it to something that doesn't work, and hopefully looking at the data in a different way will reveal something about your troubleshooting. So how can we simplify and isolate? So especially with convergence issues or very long runtimes, you can simplify your model to better identify problems and then speed up your iterations. So you can eliminate heat transfer, for example, simplify the fluid properties where we saw it go from 50 seconds to 2 seconds. We can isolate different areas using special conditions, so we can close off pipes. And then we can also consider those common pitfalls that we've been coming back to. So detailed T's, resistance curves, pumps in parallel, things like that. Specifically for impulse and extreme, you also might want to reconsider how you're sectioning and the lengths of your pipes, and that can improve your runtime. Again, in this case, when you're troubleshooting, you want to make the iteration process as quickly as possible. I want to make a change to the model, run it, see if that fixed my issue. I don't want to necessarily wait a minute or several minutes in impulse or extreme to make sure that my change is working as I intended to. The final piece is convergence, which I will leave you with a final recommendation to watch another webinar which covers this in much more detail. The big themes from that webinar is that convergence does not imply accuracy. So you want to converge on a quality solution. It has to have fine tolerances, and those fine tolerances will lead to trustworthy results. Usually it's not a good idea to try to modify that solution control to achieve convergence. So failing to converge, it's usually an indication that there's other flaws or other issues in the model. Again, consider those common pitfalls, and you can typically resolve that by modifying the model itself instead. Sometimes it can be beneficial to adjust those solution control settings. So in the cases of low flow or an arrow, you might want to change the march settings. But what's most important is you want to know what changing those settings will do to your model and ultimately how they'll change your results. So if you're really interested in how a model converges, kind of fundamentally understanding what solution control is doing and give you the confidence to modify those settings instead of doing it randomly to try to get a model to converge, because again, convergence does not imply accuracy, then I would recommend a different webinar that I put on about a year ago, talking all about solution control. The moral of the story is don't touch that unless you really know what you're doing. And there we go. We've looked at our modeling philosophy. We've looked at how to check our input is good, how we can use our output to identify those different areas, and then we can also experiment very quickly using those scenario-specific tools. So in summary, let's think about how our model can only do math. It can never tell if our input or our output is going to be accurate to the system. That relies on you, the engineer, so making sure that you're not putting garbage in, because otherwise you're only going to get garbage results out. Also, a big theme that we looked at is don't overspecify your model. You want the solver to have the flexibility to solve what it can solve for, whether that be pressure or flow rate, and how those boundary conditions can inform how your model is going to change based on different changes that you make elsewhere. Try to consider the different assumptions of your model and simplify them as you try to isolate an issue. Again, you can simplify things like fluid or heat transfer, or how pumps and resistance curves are defined. From output, if you get nothing else, be sure to read those warning messages. They're trying to tell you something. And if you ever have a question, always consult the help documentation, or you can reach out to our staff of support engineers and they can help you figure out the issue and help you troubleshoot as well. Finally, make good use of scenario-specific tools like your multi-scenario comparison, trying to isolate what variable in input that you're modifying, multi-scenario output to see the consequences of those changes, and then graphs, just another way to look at that data. And what that lets you do is perform sensitivity, and you can isolate what is making all the trouble in your model. Don't be afraid to open up a child scenario, make all the changes you want. Again, it shouldn't impact your parent scenario, and it gives you the flexibility to experiment. Especially if you've made it to this point, I want to thank everyone for attending. I know engineering time can be expensive, and committing an hour to better understanding how to use our software is really great. I'm glad that you're investing in not only yourself, but in your company and your work to make sure that you can troubleshoot your models properly. It can be a pretty complicated topic, so if you have any remaining questions about what we've gone over today, feel free to email them to webinars@aft.com, and we'll do our best to get them answered. We're also always looking for new topics for future webinars, whether that's a specific application you have, a problem you've been running into, or something specific to your industry you'd want us to cover. You can also submit a topic to webinars@aft.com. Again, I want to thank everyone for attending. Hopefully the hour was as fun for you as it was for me, and hopefully it creates some value as you look at your models going forward. If you remember nothing else, garbage in equals garbage out. Let's take out the trash and help each other out. We look forward to seeing you in the next Applied Flow Technology webinar soon enough. Thanks again.